n n by n square matrix with a real entries such that A square equal to A, and rank of A minus identity matrix equal to M, then nullity of A is what we have to find. Using rank nullity theorem, I can write nullity of A equal to n minus rank of A. So call this is an equation 1, and it is given that A square equal to A, and this is the condition or the satisfying condition or defining condition of idempotent matrix. Idempotent matrix. So A is an idempotent matrix. Then we know the relation, or you can say concept used to solve this problem is, if A is idempotent matrix, then I can write trace of A equal to rank of A. Means A square equal to A. It means that for idempotent matrix, characteristic polynomial will be x square equal to x, because we know that by using Cayley-Hamilton theorem, every matrix satisfying its characteristic polynomial. Using this concept, x square equal to x, and I can write x square minus x equal to 0. So values of x will be x equal to 0 and 1. These are the eigenvalues of matrix A. And for trace, in trace only ones will contribute, because we know that trace is sum of all eigenvalues, so there is no contribution of eigenvalues which are zeros. And for rank, we know that rank is number of non-zero eigenvalues. Rank is number of non-zero eigenvalues. Number of non-zero eigenvalues. It means that trace of A equal to rank of A. This concept is same satisfy. Now try to find the relation. Na equal to n minus rank of A, and rank of A I can replace trace of A, because of A is idempotent matrix, and I know the concept or given condition is rank of A minus identity matrix is M. So anyhow, I want to form the relation same A minus I type. So in place of n, I can write trace of identity matrix, because trace of identity matrix is n. So trace of I minus trace of A, and trace is linear function, so trace of I minus A. For this, I can write rank of I minus A, and rank of I minus A can be same as rank of A minus I, and this is given that M. So nullity of A is equal to M. C naught equal to xn, such that xn coming from real set and xn tends to 0. It means all those real sequences having limit 0, and set M defined as this means first 10 terms 0 is first 10 term sum is 0, then dimension of C naught by M is equal to, it means dimension of quotient space. First, the beauty of this question is as C naught. Here, C naught is infinite dimensional vector space. As you can see, there are infinitely many sequences which tends to 0. So infinite linearly independent sequence in C naught. So dimension of C naught equal to n. Dimension of C naught is infinite. Now this question is about the dimension of C naught quotient space. space C naught by M and asked in numerical answer type, means its answer will be a numeric value, means 2, 3, 4 and something, but dimension of C naught is infinite. It means dimension of this, maybe it is our concern, dimension of C naught is finite or infinite. But as this question asked in numerical answer type, so it is clearly understood dimension of this is finite. Also dimension of M, as dimension of M is also infinite, but whenever we relate this dimension with C naught, then its dimension will be 1 less, means dimension of C naught minus 1. Why? Because here you can see one linearly independent restriction contained in M. So dimension of M will be 1 less than dimension of C naught. If you consider C naught as n-dimensional, and n tends to infinity. So dimension of C naught is infinity, then dimension of M is less 1. Have any sense? Means infinity minus 1 is have any sense in a real system or not? This is your concern. You can think about it, but it is clearly understood dimension of M will be 1 less. Now you can justify this point as by Archimedean property. If you have any real number, then you can find a greater natural number. If you have any real number, positive real number, or if negative, then we have many natural number. But if you have any larger and larger real number, then you can find a natural number greater than that real number. So this is a point same as natural numbers are infinite and we don't know which natural number is largest, but we always can find a natural number either adding 1 or around that point. Similarly, we can justify this point. Otherwise you can stuck in this as dimension of C naught is infinite, how dimension of M will be minus 1. It has no sense, because dimension of M is also infinite, but you can justify your argument or approaches why as Archimedean property. Now come to the point, dimension of C naught over M. Dimension of C naught over M, as this is quotient space, so dimension of C naught over M will be dimension of C naught minus dimension of M. Now dimension of C naught is same as, and dimension of M is dimension of C naught minus 1. It means 1. So dimension of C naught over M means quotient space C naught over M is equal to 1. So answer of this problem is 1, and the beauty of this question is as C naught is given and M naught defined. Defining of these spaces is beautiful